Okay, welcome to my talk. My talk is Container Escape in 2021. My name is Qiang and I'm from ARMS Group. So first of all, let me introduce myself. I am a platform infrastructure security engineer at ARMS Group, and my work includes security research and security development, and my interest includes all of the low-level materials, for example, the Linux kernel, the virtualization, the container, and the security. I have been a security researcher for a long time, and I give some talks in Ruxcon, CanSecWest, and Syscon. So, okay, this is the agenda. First of all, I will talk about the container escape concept. And also this will include some of the container concept itself. As we know, container is a hot topic in nowadays. And the container security is also a hot topic in security research. As we know, there are a lot of container escape methods has been talked and discussed, but as the traditional container here, I mean runc container, share the same kernel with the host. So there are always new container escape. So in the second part, I will talk about my finding of 3 new container escape methods. This includes following. First of all, the new method is bin format Misc. The user mode help escape. Then I will talk about the EPPF escape. This is not the infamous EPPF kernel vulnerability escape methods, but the EPPF can be used to container escape itself. The final escape method is from the virtual machine monitor and after discuss the new container escape methods, I will talk about the defense. And here we can see how to defense of this new escape methods. Okay, let's go. Let's first talk about the container escape. Here I want to make it clear that in this talk, I mean container is the transition container. It means the runc container, and is made up of namespace, C group, and over the FS. The container is a lightweight OS level virtualization, and the Docker is the first implementation in industry. So I will most talk about Docker. Okay, now container is often compared with the virtualization, as they share the same virtualized runtime environment concept. Here this picture shows the virtual machine model. There is a VMM virtual machine monitor, and abstract the whole virtual machine to the virtual machine, and the virtual machine can have different operating system, and they are not aware of their runc virtual machine, and this is the container architecture. There is a Docker engine who is used to create container. Every container also has his isolated runtime environment. The most important difference between container and VM is that the container share the same kernel, and the VM has his own kernel. So share the kernel with the host is the biggest attack surface of the container security. Okay, so let's talk more about the container. Container is made up of namespace, C groups, and UniFS. The namespace is used to give different view of system resources to container. For example, the PID namespace gives the containers different PID number, and the mount namespace gives the container different mount point. The network namespace gives the container different networking stacking. The C groups is used to restrict the container's resource so that the container cannot consume a lot of the system resources. For example, the CPU and the memory resource. The UniFS is used to image share and distribution, as there are a lot of containers and they can share some of the file systems. So this is UniFS what does this. Okay, and we have said container security's root code the kernel has the biggest attack surface. This is because there is no free lunch. The container has a better performance because of share the kernel, and has less security than VM because of this share the kernel. So this makes the container and the kernel's weak isolated. So share the same kernel has been the biggest attack surface. The most severity of container security is container escape. Here, this picture shows some of the container escape methods. Mostly it can be classified with three kind of methods. The first is container engine vulnerabilities. This means this container engine has some vulnerability, so the container can leverage this vulnerability to escape to host. And the second is the privileged cap and sensitive mounts. Every process in Linux can have different capabilities. Capabilities make Linux a listed privileged system. So if the container processes has some privileged capabilities, it can leverage this to escape to the container. The sensitive mounts means that the virtual file system that mounts to container. This sensitive mounts often are virtual file system, and the kernel exports the kernel information and control options to user space. And if this file system mounts to the container can leverage this to read the kernel information and control the kernel behaviors. And as we say, the container shares the same kernel with the host, so the container can ensure syscon to the kernel to trigger the vulnerabilities in the kernel. So the kernel vulnerabilities is one of the source of container escape. Okay, here I will talk about mostly of the privileged camp and the sensitive mounts, and they are related with this talk. Here I talk about three capabilities. The first is camp session module, and we can see this camp is used to local kernel module to the kernel. So if the container has this cap, it can load a kernel module to the kernel, and can execute attributability code. This is the most severity cap. And the second is the campus admin. This campus admin has a lot of privileged operation. For example, it can use to remount the read-only mount to read-write, so that we can write the virtual file systems and control the kernel. And the third is camp.ds read search. This is used to bypass the read and search permissions. This can be used to read the host file in the container. The sensitive mounts is the virtual file system that kernel exports. Here shows the idea. It also exports the interface of the VFS, and in the container or normal process, it can read or write a prog.fs file. Mostly, the read handler will read some of the kernel information to the process, and the write handler can control kernel behavior. Okay, let's talk about user model helper program. The user model helper is used to run program from Linux kernel. Here shows the normal path create a process. The process is launched at the user space, but the user model helper is called by the kernel. For example, if the kernel decided to want to load module, it will call the user model helper model probe, and this will execute in the kernel. Kernel model helper is called by this function called user model helper. A lot of helper has used to container escape. Here is the model. So first of all, the container writer help. For example, this test.sh. This test.sh has something like can do some malicious activities. For example, you can read the shadow file and put this file in this this temp directory. Then the container process can write helper path to kernel. Here does this. And then in the host, the kernel trigger the help execve. This can be triggered from container or the other process or the other events. And then the help will be executed and read this shadow file to the container file systems. And then the container can read this shadow. Okay, this shadow is the host's it is a shadow file. This is the container escape of user model helper program. User model helper, there are a lot of user model help. For example, the model probe is used to load the module, and the call pattern is used to be called when the program has crashed. The U-event help used to the device module, and the release agent is used in C group. The bin format Misc is used to register a user space handler. This has been talked about, but as far as I know, there is no public exploit. In fact, the first method is this. Okay, then let's talk about the new container escape methods. The first is container escape through bin format Misc. Okay, that's the first introduction, the bin format Misc. It is a prog file system it is in program file system, and this bin format Misc mechanism allow kernel execute any format file to be executed. They will because the kernel can't recognize any file of this. It will call a user space program registered by the user space, and this allow attribute file format to be executed. There are a lot of use cases for this. For example, if we want to run DOS application in Linux, because Linux itself cannot execute this, but if we execute, but we register a interpreter, and then this interpreter can run our DOS application. So this mechanism can let the kernel execute any file. Let's show the example of bin format Misc. Here, first of all, we prepare a executable file. Here we create a file lambda test format, and the content is AAA. And here we can see we make it executable, and here we execute it. But let's see how the kernel will execute this. First, after we prepare this executable file, we prepare this handler. So we create a file, and we just print a test format message. And we also should make this executable. Then here we register a executable handler. This handler will match the file that begins with 3AAA. And here we can see the information, magic AAA, and then we execute the first executable, and then we can see it prints the test format message, which is the handler does. Okay, let's see the bin format internals. This is the usage case. Usage. The register interface is in this file, and we can show this with the bin format helper's name. We can clean it with 1 plus minus 1 to this. Here is the field of the data we need to register. The type means we recognize the file with magic or extension. Here with magic. And the offset means where we start to do the match work. And the magic is the data match. And the mask is used to show which byte this is valid. And the interpreter is the most important. This is the full path of the interpreter and will be called by the kernel. Here we can say the interpreter is this, and he will interpret the file with AAA at the beginning. Let's see the bin format Misc internals. Next kernel meant format list. This list register a lot of formats that the kernel can execute. For example, the batch, the ELF format. When we does execve source code, the kernel will search the list, and if one format has been found that match the executable file, the load button will be called, and the file will be executed. Okay, so let's say bin format Misc in this list. The Misc format entry is inserted into the head of the format. here we can say the heads. So if two handlers match the same executable file, the Misc format is selected. This means if, for example, this format this entry is used to process ELF. This entry is used to process batch file. But if we registered a more precious match, and if the search process finds that our bin format is matched, and it will call our handler. So this means that we can insert a new executable handler for ELF and batch. This shows the idea. First of all, we can register a handler, interpreter here in the container file systems, and it's red shadow and put here. Then the process can register a format handler, and then now the kernel has this format handler. The kernel executes, for example, if someone executes the file in the host, and then our interpreter will be called, and it will read the shadow of the host and write it to the container file system. So this is the POC of the container escape through bin format Misc. Here we set this interpreter handler as this. So it just read shadow and put this file in the shadow. And here we register a handler with this. This offset means at the start, match the file at the start. This magic means that the file which is used, which begins with this strings will be matched to our handler, and the interpreter is this. So in our container, and so the host we can prepare a host bench. Here we can see this bench this bench file is matched with our pattern. It begins with this string and equal. So when the host executes this file, the kernel searches the format list, and it will find our bin format Misc is matched. So the interpreter will be executed, and it will read the shadow file and write it to the file systems. So the container can read this shadow. This shadow is the host shadow file. Okay, here is the picture of how it does. Here we start a container, and notice we need to and CanSecWest. So here we remount the remount the probe size FS from read only to read write. And here we found that the file system of the container. And here we write the helper, and here we register the interpreter. So in the host we execute a matched file, and we can say it did nothing. It did nothing, just read etc shadow and write. So in the step 3, we can see that the temp directory has the shadow file, and we get the host file. Okay, this is the second example of bin format Misc. Here just example for replace the ELFL handler. So we can see the LS program on hex, and we found that in here we have 2 bytes. So we use this 2 as a match, and we register a handler for this file. So when the host executes ls, we can see that the container contains the shadow file. So this shows that we can replace the ELFL handler. Okay, so let's talk about the second escape methods, escape through EPPF. Also, let's first introduce the EPPF concept. EPPF is short for Extended Berkeley Packet Filtering. It is originated from CanSecWest in 1992. It initially is used for packet filtering, but now it's used in a lot of places. It and restricted code to kernel and runtime. EPPF has grown in recent years very fast. Just like what JavaScript does for browser, the EPPF also enriches a lot of kernel innovation. EPPF has a lot of use cases. For example, the networking, the chasing, the runtime security. The first use case for EPPF is in networking. For example, you can replace the IP tables with EPPF, and also the chasing is a important use case for EPPF. And recently, the EPPF used in the runtime security. For example, the focus is used to detect the malicious activities in the container and the host. Okay, this is the architecture of EPPF. First of all, we program EPPF programs and maps, and then the LLVM compiler will compile this source file to bytecode, and we can use BPF Syscon to load this program maps to kernel, and the kernel will verify that our BPF has no harm to system, and sometimes it will compile it from the EPPF instruction to the machine native instruction, and so we have EPPF valid EPPF program. Then it will be attached to a system called networking, Kprop, and LSM, and the other subsystems. Also, there is maps and helpers. Okay, some of the core concepts I need to explain here. EPPF program type is where EPPF will be executed. So when the kernel runs at the EPPF point, the kernel point EPPF program will be executed. The EPPF map. This is used to do communication between the kernel and the user space. Also, the EPPF map can be used between the EPPF programs, different program types. EPPF verifier is used to make EPPF program has no harm to the kernel. For example, the stack usage of EPPF program is very limited. EPPF help, this is just like library, and the EPPF program can call this library to do his own work. Okay, let's talk about the Kprop and EPPF. Kprop is a measurement that can be used to instrument the kernel and almost any kernel code address. There are two Kprop. kprob types, the kprob which is used to which is instrumentation and the point, and the caret prob is used to instrumentation and the function return point. The eBPF program can be attached to kprob. So here shows the idea. For example, if we attach eBPF to the kprob of kernel function and the caret prob also to this kernel function, the call path should be this: when the kernel calls this function, our first eBPF program will be executed, and then the kernel function, and then the caret prob eBPF program. The eBPF program can print data to the transfer pipe or the perf buffer. Okay, let's talk about container and eBPF. Container, both eBPF and kprob is not aware of the C group and lamp, so they are system wide. So if the container has camp size admin or camp BPF, it can load the eBPF program in kernel. Notice this is system wide. So the container can read or control system level behavior. So here shows the container escape through eBPF. So the container first attach a eBPF program in the VFS read caret prob, and then the host read, when the host read etc shadow or any file, the VFS read will be called, and it will read etc shadow, and between its return, it will call our eBPF program. In this place, the eBPF can read the data what the VFS read have loaded, and so the container will get this data. So here shows the concrete POC. So first of all, the container attach caret prob to this, and then it read the transfer pipe, and when VFS read etc shadow, it will load the data into memory. And some register will point to this. For example, R 13, and so the eBPF program can read from this register and print this buffer to the container. Here shows the concept. Here shows the POC picture. Also, first of all, we start a container with sysadmin, and then we mount transfs. Here we create a caret prob of VFS read, and we load this program. We load this eBPF program in kernel. So in the second terminal, we read this transfer pipe file, and in host we can read etc shadow file, and we can see here we read the file of the etc shadow. So this demonstrates the container escape through eBPF. In fact, there are several topics about eBPF can be used as a rootkit. For example, they can read the host file. They can hijack the execution. So here is this just a POC to demonstrate that we can escape through eBPF. Okay, let's go to the final methods of container escape. Escape from virtual machine monitor. Nowadays, the container is often run in a VM, and so they can benefit from both architecture. For example, the VM can be used in very a flexible way, and the container is also. So here we often see an architecture with this, the QEMU virtual machine and the runc container. But we need to know that the VM attack surface has vulnerabilities. The interface between VMs and QEMU devices is a lot of vulnerabilities. So the VM can write a lot of data to the devices, and if this VM has vulnerabilities, the VM can trigger this. This is a typical virtual machine monitor vulnerabilities. The Linux kernel exports device and driver sets when the driver information through SysFS. This SysFS is like also a virtual file system like progfs. It's usually mounted at the site, and it contains device and driver information and can control device behavior. For example, this is a typical information about the device information. Here we can see that it has a PIC configuration. It is write and read. Also, the resource 012 is MMIO resources. It is also read right. So here we can see the devices, the driver in the VM can trigger vulnerabilities in QEMU through MMIO. So if we export this SysFS to the container, it can also trigger the vulnerabilities through user space by writing this MMIO. So here shows the idea. And the container can interact with the device through the SysFS. Of course, if we need to campsite admin to mount SysFS and remount the SysFS from read only to read write. And if the virtual device is variable, so we can read and write the MMIO of the device in container through SysFS interface. So here the POC I used is changed from the scavenger from Pangolin and Lingxingwei. Just the POC changed from here. I just changed this. So here shows. First of all, I start a QEMU virtual machine this, and then I run a container, and I give this campsite admin capabilities, and then I install some of the package, the build package. Then in the QEMU VM, I mount the SysFS from the read only to read write. Then we execute the exploit. Then in the host QEMU process, I give a call. The QEMU process crashed. So this here this what here I see what it does. So in the container, we trigger the vulnerabilities then QEMU through the SysFS. We write the MMIO and trigger the vulnerabilities in QEMU. So the QEMU crashes. And this topic is not about VM escape, so I will not show this in our total. So just a POC that can demonstrate the idea. So let's talk about how we can defend of this. And we can say the bin format Misc is a common user model helper is escape. So there are several methods to defense of this attack. The first is using secure container. For example, the gvisor kata, because secure container has a separate kernel for the container. So if they will not share the kernel with the host, they can't can't change the host's user mode help. Then we can drop CanSecWest. So this way, we can't remount the prog fs. We can also use the user mode help whitelist. For example, the kernel contains a configuration for this. Also, if we have used the LSM in production, we can also open them. Okay, for the EPPF escape, also first of all, we can drop the CanSecWest, can't remount. Then we can disable unprivileged container of the EPPF. This is not an upstream solution. Then we can also just allow the signed EPPF program to be loaded into kernel. This is in progress. In fact, the EPPF program escape has been demonstrated as a very powerful. So we need to harden this. For the VMM escape, also we can security container through secure container, and as the vulnerabilities in the container itself don't infect the whole system. Also, we can drop the CanSecWest, so this we cannot remount the file system. Also, we need to track and fix the virtual machine monitor vulnerabilities. Okay, this is all my talk. In this talk, I have talked about 3 new methods on a container escape. The user mode help is exploit, and the container escape through EPPF is used to container escape through EPPF program. And finally, we need to also focus the security of virtual machine monitor who as the infrastructure as run container. Thank you.